what highlight is? It's like that like shit you put on your face to like make it glowy, like glisten. Okay, what's a makeup thing? And she was like, "Oh my god, your highlight looks so good." And I was like, "Thank you," but I wasn't wearing any makeup. It was just my sweat. Can you push me this way? A little bit.
This way?
Like away. Too far. What?
All right.
Oh, do you want to see what I'm supposed to say to you in game? Curtis gave me this Riz tactic. I need to spill some milk on my chest, and then I have to say, "You know what, Ming? I really enjoy it if you sucked the milk out of my and called me mommy. Yeah, you like that mommy milk, Ming? It's nutritious."
That's a good one, Curtis.
Se siente como si estoy manejando un carro de lujo, la verdad. Mi nombre es Romario Ávila, manejo un Toyota Camry.
Ahora elige entre grandes ofertas como estas en un nuevo y atrevido Camry. Lo hacemos fácil. Toyota, vayamos juntos.
Boys! You ever lie? I do sometimes. I've never told you this, but occasionally when I say, "Hey, can you guys subscribe?" Sometimes it unsubscribes people. I lied to deceive you into wanting to subscribe or check to see if you still are. When you guys ask me if I've washed my hands, I say yes, but I never do. These are the common white lies that I spread throughout the day. It's a normal part of life, these little tattletales we spread. But how far does it really go? And what are the main things that people lie about? Well, that is what I wanted to find out. So I made a little bit of a test. I asked my Twitch chat 9 questions about what they lie about, and let's see how they feel. Let's see what they're willing to lie about. And before we jump into it, boys, do me a favor, subscribe. And if you aren't, just double check to see if you have subbed. And say out loud if you have, "I subbed." Don't keep watching the video. Don't lie to me. Just double check. You can even choose not to, but just hit the subscribe button first, you know what I mean? Like if you don't want to subscribe, hit the subscribe button and then unsubscribe. I'm not telling you to unsubscribe, by the way. I'm just saying to hit it and then unsubscribe if you don't want to subscribe. Not that you should hit the button. You probably shouldn't hit. I regret saying this at all. Let's get to it. This is a survey I made. 3,500 people responded to it, and it asks 9 questions, 9 very basic questions about general daily things that you might lie about. And I asked my chat how they felt about it. First question was, do you wash your hands after peeing in your own house? Is the key signifier. Because, look, I get it. If you're out and about, especially mid-COVID, you should be washing your hands. Even if you're not peeing, you touch a doorknob and you're out and about, you should probably wash your hands. Otherwise, you're risking getting sick. But if you're in your own home with your own toilet, in your own shower, in your own pee-pee, in your own bathroom, do you really need to wash them? I'll answer all of these honestly. I don't even have soap in my bathroom. I haven't had soap in my bathroom for 3 months. I used to wash them daily. I used to, and because chat bullied me was the only reason. And then I had a soap bar, and it ran out of soap because that's how soap bars work. And I haven't done it. If I go poop, I use shampoo from the shower next to my bathtub or next to my toilet. I don't know if that counts. I use shampoo. Does that count? The cowgirls make do. Without Cutie, I am useless. You guys need to understand this. Does this make it better? Wait, I pee while sitting down. Huh? Come on. I literally am like a genie. I hover over to the toilet, I sit down, and then I piss. And then I stand up and I pull up my pants, and then I leave. What am I washing my hands for? If I poop, I will wash them. I have some class. If I'm pooping, I will wash them. But I also have a bidet. I don't even need to touch toilet paper.
With Fargo, the new virtual assistant from Wells Fargo, you can instantly know what you spend on things like food.
Fargo, what did I spend on groceries this month?
Hey, Dad, can the guy stay for dinner?
No.
Want faster, easier banking? You can with Wells Fargo.
Janet has a sponsor at 5 p.m. with Peter.
Oh, Peter? That's crazy. On the stream yesterday, we said if we were friends, we'd all be there at 5 p.m. tomorrow.
That's today, not tomorrow.
Oh, the sponsor's today.
That would have been so funny, though.
That guy's causing drama.
Janet has a sponsor at 5 p.m. with Peter.
Oh, Peter? That's crazy. On the stream yesterday, we said if we were friends, we'd all be there at 5 p.m. tomorrow.
That's today, not tomorrow.
Oh, the sponsor's today.
That would've-
Your health is your biggest asset. Find Anthem Blue Cross plan starting at $0 a month. Apply in 5 to 10 minutes for a secure future at Health for California.
If you're taking a trip with your friends, why pay for 4 hotel rooms to stay apart?
money buying beans when you should have been getting an Icon Pass. I'm the deal you
is by far the best low carb turkey bacon club I have ever had, and it's made with one of my favorite alternative breads, Hero. Not only
You want to be a software engineer, right? Go to algoacademy.com. Use our step-by-step coding tutorial.
This is a video about one of the most important, yet least understood, concepts in all of physics. It governs everything from molecular collisions to humongous storms, from the beginning of the universe through its entire evolution to its inevitable end. It may in fact determine the direction of time and even be the reason that life exists. To see the confusion around this topic, you need ask only one simple question. What does the Earth get from the sun?
What does the Earth get from sun?
Well, it's light rays.
What do we get from the
Heat.
sun?
Warmth.
Warmth, light.
Vitamin D. We get vitamin D from.
We do get vitamin D from the ultraviolet rays.
Well, a lot of energy.
What does the Earth get from this energy?
Yeah, it's energy.
Energy.
Nailed it. Every day the Earth gets a certain amount of energy from the sun, and then how much energy does the Earth radiate back into space relative to that amount that it gets from the sun?
Probably not as much. I don't believe it. It's just radiating right back.
I'd say less.
Less.
I would
say less.
I'd guess about 70%.
I think it's a fraction. I'd say 20%.
Because
we use some of it.
we use some of the energy.
We consume a lot, right?
But the thing about energy is it never really goes away. You can't really use it up.
It would have to break even, wouldn't it? Same amount, yeah.
You know, cause and effect, it'd be equal in some ways, right?
For most of the Earth's history, it should be exactly the same amount of energy in from the sun as Earth radiates into space.
Wow.
Because if we didn't do that, then the Earth would get a lot hotter. That'd be a problem.
That'd be a big problem.
So if that is the case, then what are we really getting from the sun?
That's a good question.
It gives us a nice tan.
It gives us a nice tan. I love it. We're getting something special from the sun.
I don't know. What do we get without the energy?
But nobody talks about it.
To answer that, we have to go back to a discovery made 2 centuries ago. In the winter of 1813, France was being invaded by the armies of Austria, Prussia, and Russia. The son of one of Napoleon's generals was Sadi Carnot, a 17-year-old student. On December 29th, he writes a letter to Napoleon to request to join in the fight. Napoleon, preoccupied in battle, never replies. But Carnot gets his wish a few months later when Paris is attacked. The students defend a chateau just east of the city. But they're no match for the advancing armies, and Paris falls after only a day of fighting. Forced to retreat, Carnot is devastated. 7 years later, he goes to visit his father, who's fled to Prussia after Napoleon's downfall. His father was not only a general, but also a physicist. He wrote an essay on how energy is most efficiently transferred in mechanical systems. When his son comes to visit, they talk at length about the big breakthrough of the time, steam engines. Steam engines were already being used to power ships, mine ore, and excavate ports. And it was clear that the future industrial and military might of nations depended on having the best steam engines. But French designs were falling behind those of other countries, like Britain, so Sadi Carnot took it upon himself to figure out why. At the time, even the best steam engines only converted around 3% of thermal energy into useful mechanical work. If he could improve on that, he could give France a huge advantage and restore its place in the world. So he spends the next 3 years studying heat engines. And one of his key insights involves how an ideal heat engine would work, one with no friction and no losses to the environment. It looks something like this. Take 2 really big metal bars, one hot and one cold. The engine consists of a chamber filled with air, where heat can only flow in or out through the bottom. Inside the chamber is a piston, which is connected to a flywheel. The air starts at a temperature just below that of the hot bar. So first, the hot bar is brought into contact with the chamber. The air inside expands with heat flowing into it to maintain its temperature. This pushes the piston up, turning the flywheel. Next, the hot bar is removed, but the air in the chamber continues to expand. Except now, without heat entering, the temperature decreases, in the ideal case until it is the temperature of the cold bar. The cold bar is brought into contact with the chamber and the flywheel pushes the piston down. And as the air is compressed, heat is transferred into the cold bar. The cold bar is removed, the flywheel compresses the gas further, increasing its temperature until it is just below that of the hot bar. Then the hot bar is connected again, and the cycle repeats. Through this process, heat from the hot bar is converted into the energy of the flywheel. And what's interesting to note about Carnot's ideal engine is that it is completely reversible. If you ran the engine in reverse, first the air expands, lowering the temperature, then the chamber is brought into contact with the cold bar, the air expands more, drawing in heat from the cold bar. Next, the air is compressed, increasing its temperature. The chamber is placed on top of the hot bar, and the energy of the flywheel is used to return the heat back into the hot bar. However many cycles were run in the forward direction, you could run the same number in reverse, and at the end, everything would return to its original state, with no additional input of energy required. So by running an ideal engine, nothing really changes. You can always undo what you did. So what is the efficiency of this engine? Since it's fully reversible, you might expect the efficiency to be 100%. But that is not the case. Each cycle, the energy of the flywheel increases by the amount of heat flowing into the chamber from the hot bar, minus the heat flowing out of the chamber at the cold bar. So to calculate the efficiency, we divide this energy by the heat input from the hot bar. Now the heat in on the hot side is equal to the work done by the gas on the piston, and this will always be greater than the work done by the piston on the gas on the cold side, which equals the heat out. And this is because on the hot side, the hot gas exerts a greater pressure on the piston than that same gas when cold. To increase the efficiency of the engine, you could increase the temperature of the hot side, or decrease the temperature of the cold side, or both.
Hi, my name's Hannah, and I'm here to show you how students can use Otter to make lectures and campus events more accessible and inclusive. As you can see,
Lord Kelvin learns of Carnot's ideal heat engine and realizes it could form the basis for an absolute temperature scale. Imagine that the gas is allowed to expand an extreme amount, so much that it cools to the point where all the gas particles effectively stop moving. Then they would exert no pressure on the piston, and it would take no work to compress it on the cold side, so no heat would be lost. This is the idea of absolute zero, and it would make for a 100% efficient engine. Using this absolute temperature scale, the Kelvin scale, we can replace the amount of heat in and out with the temperature of the hot and cold side respectively, because they are directly proportional. So we can express efficiency like this, which we can rewrite like this. What we have learned is that the efficiency of an ideal heat engine doesn't depend on the materials or the design of the engine, but fundamentally on the temperatures of the hot and cold sides. To reach 100% efficiency, you'd need infinite temperature on the hot side or absolute zero on the cold side, both of which are impossible in practice. So even with no friction or losses to the environment, it's impossible to make a heat engine 100% efficient. And that's because to return the piston to its original position, you need to dump heat into the cold bar, so not all the energy stays in the flywheel. Now, in Carnot's time, high-pressure steam engines could only reach temperatures up to 160 degrees Celsius, so their theoretical maximum efficiency was 32%, but their real efficiency was more like 3%. That's because real engines experience friction, dissipate heat to the environment, and they don't transfer heat at constant temperatures. So for just as much heat going in, less energy ends up in the flywheel. The rest is spread out over the walls of the cylinder, the axle of the flywheel, and is radiated out into the environment. When energy spreads out like this, it is impossible to get it back. So this process is irreversible. The total amount of energy didn't change, but it became less usable. Energy is most usable when it is concentrated, and less usable when it's spread out. Decades later, German physicist Rudolf Clausius studies Carnot's engine, and he comes up with a way to measure how spread out the energy is. He calls this quantity entropy. When all the energy is concentrated in the hotbar, that is low entropy. But as the energy spreads to the surroundings, the walls of the chamber and the axle, well, entropy increases. This means the same amount of energy is present, but in this more dispersed form, it is less available to do work. In 1865, Clausius summarizes the first two laws of thermodynamics like this. First, the energy of the universe is constant. And second, the entropy of the universe tends to a maximum. In other words, energy spreads out over time. The second law is core to so many phenomena in the world. It's why hot things cool down and cool things heat up, why gas expands to fill a container, why you can't have a perpetual motion machine, because the amount of usable energy in a closed system is always decreasing. The most common way to describe entropy is as disorder, which makes sense because it is associated with things becoming more mixed, random, and less ordered. But I think the best way to think about entropy is as the tendency of energy to spread out. So why does energy spread out over time? I mean, most of the laws of physics work exactly the same way, forwards or backwards in time. So how does this clear time dependence arise? Well, let's consider two small metal bars, one hot and one cold. For this simple model, we'll consider only 8 atoms per bar. Each atom vibrates according to the number of energy packets it has. The more packets, the more it vibrates. So let's start with 7 packets of energy in the left bar and 3 in the right. The number of energy packets in each bar is what we'll call a state. First, let's consider just the left bar. It has 7 energy packets which are free to move around the lattice. This happens non-stop. The energy packets hop randomly from atom to atom, giving different configurations of energy. But the total energy stays the same the whole time. Now let's bring the cold bar back in with only 3 packets and touch them together. The energy packets can now hop around between both bars, creating different configurations. Each unique configuration is equally likely. So what happens if we take a snapshot at one instant in time and see where all the energy packets are? So stop. Look at this. Now there are 9 energy packets in the left bar and only 1 in the right bar. So heat has flowed from cold to hot. Shouldn't that be impossible because it decreases entropy? Well, this is where Ludwig Boltzmann made an important insight. Heat flowing from cold to hot is not impossible, it's just improbable. There are 91,520 configurations with 9 energy packets in the left bar, but 627,264 with 5 energy packets in each bar. That is, the energy is more than 6 times as likely to be evenly spread between the bars. But if you add up all the possibilities, you find there's still a 10.5% chance that the left bar ends up with more energy packets than it started. So why don't we observe this happening around us? Well, watch what happens as we increase the number of atoms to 80 per bar and the energy packets to 100, with 70 in the left bar and 30 in the right. There is now only a 0.05% chance that the left solid ends up hotter than it started. And this trend continues as we keep scaling up the system. In everyday solids, there are around 100 trillion atoms and even more energy packets. So heat flowing from cold to hot is just so unlikely that it never happens.
Think of it like this Rubik's Cube. Right now, it is completely solved, but I'm going to close my eyes and make some turns at random. If I keep doing this, it will get further and further from being solved. But how can I be confident that I'm really messing this cube up? Well, because there's only one way for it to be solved, a few ways for it to be almost solved, and quintillions of ways for it to be almost entirely random. Without thought and effort, every turn moves the Rubik's Cube from a highly unlikely state, that of it being solved, to a more likely state, a total mess. So if the natural tendency of energy is to spread out and for things to get messier, then how is it possible to have something like air conditioning, where the cold interior of a house gets cooler and the hot exterior gets hotter? Energy is going from cold to hot, decreasing the entropy of the house. Well, this decrease in entropy is only possible by increasing the entropy a greater amount somewhere else. In this case, at a power plant, the concentrated chemical energy in coal is being released, heating up the power plant and its environment, spreading to the turbine, the electric generators, heating the wires all the way to the house, and producing waste heat in the fans and compressor. Whatever decrease in entropy is achieved at the house is more than paid for by an increase in entropy required to make that happen. But if total entropy is constantly increasing, and anything we do only accelerates that increase, then how is there any structure left on Earth? How are there hot parts separate from cold parts? How does life exist? Well, if the Earth were a closed system, the energy would spread out completely, meaning all life would cease, everything would decay and mix, and eventually reach the same temperature. But luckily, Earth is not a closed system, because we have the sun. What the sun really gives us is a steady stream of low entropy, that is, concentrated, bundled up energy. The energy that we get from the sun is more useful than the energy we give back. It's more compact, it's more clumped together. Plants capture this energy and use it to grow and create sugars. Then animals eat plants and use that energy to maintain their bodies and move around. Bigger animals get their energy by eating smaller animals, and so on. And each step of the way, the energy becomes more spread out.
Okay, interesting.
Yeah. Oh, wow. I did not know that.
There you go. Ultimately, all the energy that reaches Earth from the sun is converted into thermal energy, and then it's radiated back into space. But in fact, it's the same amount. I know this is
You do know this is...
I'm a PhD physicist.
Oh, okay.
But
Okay.
anyway,
I trust you.
The increase in entropy can be seen in the relative number of photons arriving at and leaving the Earth. For each photon received from the sun, 20 photons are emitted. And everything that happens on Earth, plants growing, trees falling, herds stampeding, hurricanes and tornadoes, people eating, sleeping, and breathing, all of it happens in the process of converting fewer higher energy photons into 20 times as many lower energy photons. Without a source of concentrated energy and a way to discard the spread out energy, life on Earth would not be possible. It has even been suggested that life itself may be a consequence of the second law of thermodynamics. If the universe tends toward maximum entropy, then life offers a way to accelerate that natural tendency, because life is spectacularly good at converting low entropy into high entropy. For example, the surface layer of seawater produces between 30 to 680% more entropy when cyanobacteria and other organic matter is present than when it's not. Jeremy England takes this one step further. He's proposed that if there is a constant stream of clumped up energy, this could favor structures that dissipate that energy. And over time, this results in better and better energy dissipators, eventually resulting in life. Or, in his own words, you start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant. So, life on Earth survives on the low entropy from the sun. But then, where did the sun get its low entropy? The answer is the universe.
if we know that the total entropy of the universe is increasing with time, then it was lower entropy yesterday, and even lower entropy the day before that, and so on all the way back to the Big Bang. So right after the Big Bang, that is when the entropy was lowest. This is known as the past hypothesis. It doesn't explain why the entropy was low, just that it must have been that way for the universe to unfold as it has. But the early universe was hot, dense, and almost completely uniform. I mean, everything was mixed and the temperature was basically the same everywhere, varying by at most 0.001%. So how is this low entropy? Well, the thing we've left out is gravity. Gravity tends to clump matter together. So taking gravity into account, having matter all spread out like this would be an extremely unlikely state, and that is why it's low entropy. Over time, as the universe expanded and cooled, matter started to clump together in more dense regions, and in doing so, enormous amounts of potential energy were turned into kinetic energy. And this energy could also be used, like how water flowing downhill can power a turbine. But as bits of matter started hitting each other, some of their kinetic energy was converted into heat, so the amount of useful energy decreased, thereby increasing entropy. Over time, the useful energy was used. In doing so, stars, planets, galaxies, and life were formed, increasing entropy all along. The universe started with around 10 to the 88 Boltzmann constants worth of entropy. Nowadays, all the stars in the observable universe have about 9.5 times 10 to the 80. The interstellar and intergalactic medium combined have almost 10 times more, but still only a fraction of the early universe. A lot more is contained in neutrinos and in photons of the cosmic microwave background. In 1972, Jacob Bekenstein proposed another source of entropy: black holes.
When you're confident, you're inspired to take the road less traveled. Am I supposed to be somewhere? Mitsubishi Motors delivers confidence every day with their new integrated care program. 2 years of included maintenance, an industry-leading warranty, and it's standard on all new 2024.
He suggested that the entropy of a black hole should be proportional to its surface area. So as a black hole grows, its entropy increases. Famous physicists thought the idea was nonsense, and for good reason. According to classical thermodynamics, if black holes have entropy, then they should also have a temperature. But if they have temperatures, they should emit radiation and not be black after all. The person who set out to prove Bekenstein wrong was Stephen Hawking. But to his surprise, his results showed that black holes do emit radiation, now known as Hawking radiation, and they do have a temperature. The black hole at the center of the Milky Way has a temperature of about 100 trillionth of a Kelvin, emitting radiation that is far too weak to detect, so still pretty black. But Hawking confirmed that black holes have entropy, and Bekenstein was right. Hawking was able to refine Bekenstein's proposal and determine just how much entropy they have. The supermassive black hole at the center of the Milky Way has about 10 to the 91 Boltzmann constants of entropy. That is 1,000 times as much as the early observable universe, and 10 times more than all the other particles combined. And that is just one black hole. All black holes together account for 3 times 10 to the 104 Boltzmann constants worth of entropy. So almost all the entropy of the universe is tied up billion black holes. That means the early universe only had about 0.000000000000003% of the entropy it has now. So the entropy was low, and everything that happens in the universe, like planetary systems forming, galaxies merging, asteroids crashing, stars dying, to life itself flourishing, all of that can happen because the entropy of the universe was low and it has been increasing. And it all happens only in one direction. We never see an asteroid uncrash or a planetary system unmix into the cloud of dust and gas that made it up. There is a clear difference between going to the past and the future, and that difference comes from entropy. The fact that we are going from unlikely to more likely states is why there is an arrow of time. This is expected to continue until eventually the energy gets spread out so completely that nothing interesting will ever happen again. This is the heat death of the universe. In the distant future, more than 10 to the 100 years from now, after the last black hole has evaporated, the universe will be in its most probable state. Now, even on large scales, you would not be able to tell the difference between time moving forwards or backwards, and the arrow of time itself would disappear. So it sounds like entropy is this awful thing that leads us inevitably towards the dullest outcome imaginable. But just because maximum entropy has low complexity does not mean that low entropy has maximum complexity. It's actually more like this tea and milk. I mean, holding it like this is not very interesting. But as I pour the milk in, the two start to mix, and these beautiful patterns emerge. They arise in an instant, and before you know it, they're gone, back to being featureless. Both low and high entropy are low in complexity. It's in the middle where complex structures appear and thrive. And since that's where we find ourselves, let's make use of the low entropy we've got while we can. With the right tools, we can understand just about anything, from a cup of tea cooling down to the evolution of the entire universe. And if you're looking for a free and easy way to add powerful tools to your arsenal, then you should check out this video's sponsor, Brilliant.org. With Brilliant, you can master key concepts in everything from math and data science to programming and physics. All you need to do is set your goal, and Brilliant will design the perfect learning path for you, equipping you with all the tools you need to reach it. Want to learn how to think like a programmer? Then Brilliant's latest course, Thinking in Code, is a fast and easy way to get there. Using an intuitive drag-and-drop editor, it teaches you what you really need to know, including essential concepts like nesting and conditionals. You can start by jumping right in to program a robot, and then learn how to apply your new tools to your everyday life, like automating reminders on your phone or building a bot that filters your matches on a
Every month, this Airbnb pays me in semi-passive income. Now, here's the thing. I don't own it, and I don't pay any rent. It doesn't even matter where you live, even if you're...
This is a video about the oldest unsolved problem in math. It dates back 2,000 years. Some of the brightest mathematicians of all time have tried to crack it, but all of them failed.
In the year 2000, the Italian mathematician Pier Giorgio Odefreddi listed it among 4 of the most pressing open problems at the time.
Solving this problem could be as simple as finding a single number. So mathematicians have used computers and checked numbers up to 10 to the power of 2,200. But so far they've come up empty-handed.
Why do you think this problem has captured the imaginations of so many mathematicians?
It's old. It's simple. It's beautiful.
What else could you want?
So the problem is this. Do any odd perfect numbers exist? So what is a perfect number?
Well, take the number 6, for example. You can divide it by 1, 2, 3, and 6. But let's ignore 6 because that's the number itself. And now we're left with just
If you have polarized sunglasses, you have a quantum measurement device.
Each of these pieces of glass is what's called a polarizing filter, which means when a photon of light reaches the glass, it either passes through or it doesn't. And whether or not it passes through is effectively a measurement of whether or not that photon is polarized in a given direction.
Try this. Find yourself several sets of polarized sunglasses or old photographic filters. Look through one set of sunglasses at some light source, like a lamp, then hold a second polarizing filter between you and the light. As you rotate that second filter, the lamp will look lighter and darker. It should look darkest when the second filter is oriented 90 degrees off from the first. What you're observing is that the photons with polarization that allows them to pass through a filter along one axis have a much lower probability of passing through a second filter along a perpendicular axis. In principle, zero probability.
But here's where things get quantumly bizarre. All these filters do is remove light. They filter it out. But if you take a third filter and orient it 45 degrees off from that first one, and then you put it in between the two, the lamp actually looks brighter. This is not the middle filter generating more light. Somehow, introducing another filter actually lets more light through. With perfect filters, if you keep adding more and more in between at in-between angles, this trend actually continues. More light.
This feels super weird, but it's not just weird that more light comes through. When you dig in quantitatively to exactly how much more light comes through, the numbers don't just seem too high, they seem impossibly high. And when we tug at this thread, it leads to an experiment a little more sophisticated than this sunglasses demo that forces us to question some very basic assumptions we have about the way the universe works. Like that the results of experiments describe properties of the thing you're experimenting on, and that cause and effect don't travel faster than the speed of light. These will come into question.
Where we're headed is Bell's theorem, one of the most thought-provoking discoveries in modern physics. And to appreciate it, I really do think it's worth understanding a little of the math that we use to represent quantum states, like the polarization of a photon. And we actually made a second video showing more of the details for how this works, which you can find on 3Blue1Brown. But right now, let's just go ahead and hit the main points. First, photons are waves. Waves in a thing called the electromagnetic field. And polarization just means the direction in which that wave is wiggling. Polarizing filters absorb this wiggling energy along one direction so that the wave coming out on the other side is wiggling purely in the direction perpendicular to the one where the energy absorption is happening. But unlike a water wave or a sound wave, photons are quantum objects, and as such, they either pass through the polarizer completely or not at all. And this is apparently probabilistic, like how we don't know whether or not Schrodinger's cat will be alive or dead until we look into the box.
For anyone uncomfortable with the non-determinism of quantum mechanics, it's tempting to imagine that a probabilistic event like this might have some deeper cause that we just don't know yet. That there's some hidden variable describing the photon's state that would tell us with certainty whether it should pass through a given filter or not. And maybe that variable is just too subtle for us to probe without deeper theories and better measuring devices. Or maybe it's somehow fundamentally unknowable, but still there. The possibility of such a hidden variable seems beyond the scope of experiment. I mean, what measurements could possibly probe at a deeper explanation that might or might not exist? And yet, we can do just that.
With sunglasses and polarization of light. Let's go ahead and lay down some numbers here. When light passes through a polarizing filter oriented vertically and then comes to another polarizing filter oriented that same way, experiments show that it's essentially guaranteed to make it through that second filter. But if that second filter was tilted 90 degrees from the first, then each photon has a 0% chance of passing through. And halfway between, at 45 degrees, there's a 50-50 chance.
What's more, these probabilities seem to only depend on the angle between the two filters in question, and not on anything that happened to the photon before, including potentially having passed through a different filter first.
But the real numerical weirdness here happens for filters oriented less than 45 degrees apart. For example, at 22.5 degrees, any photon which passes through that first filter has an 85% chance of passing through the second filter. To see where all these numbers come from, by the way, check out the second video.
What's strange about that last number is that you might expect it to be more like halfway between 50% and 100%, since 22.5 degrees is halfway between 0 and 45, but 85% is significantly higher. To see concretely how strange this is, let's look at a particular arrangement of our three filters. A, oriented vertically, B, oriented 22.5 degrees from vertical, and C, oriented 45 degrees from vertical. We're going to compare just how many photons get blocked when B isn't there with how many get blocked when B is there. When B is not there, half of those passing through A get blocked at C. That is, filter C makes the lamp look half as bright as it would with just filter A. But once you insert B, 85% of those passing through A pass through B, which means 15% are blocked at B, and 15% of those that pass through B are blocked at C. But how on earth does blocking 15% twice add up to the 50% blocked if B isn't there? Well, it doesn't, which is why the lamp looks a lot brighter when you insert filter B. But it really makes you wonder how the universe is deciding which photons to let through and which ones to block.
In fact, these numbers suggest that it's impossible for there to be some hidden variable determining each photon's state with respect to each filter. In other words, it suggests that it's not even possible for these photons to have some definite answer to the three questions: would it pass through A, would it pass through B, and would it pass through C, before those measurements are actually made. What we'll do here is a proof by contradiction. Imagine 100 photons who do have some hidden variable, which through whatever crazy underlying mechanism you might imagine, determines their answers to these questions. And let's say that all of these definitely pass through A, which I'll show by putting all 100 inside this circle, representing photons that pass through A. Now, if you want to produce the results that you see in experiments, about 85 of these photons would have a hidden variable determining that they pass through B. So let's put 85 of these guys inside the intersection of circles A and B, leaving 15 in this crescent moon section representing photons that pass through A but get blocked at B. Similarly, among those 85 that would pass through B, about 15% of them should get blocked at C, which is represented in this little section here that's inside circle A and B, but outside circle C. So the actual number whose hidden variable has them passing through both A and B, but not C, is certainly no more than 15. But now think of what Henry was just saying. What was weird was that when you remove filter B, never asking those photons what they think about 22.5 degree angles, the number that get blocked at C seems too high. So let's take a look back at our Venn diagram. What does it mean if one of these photons has some hidden variable determining that it should pass A but get blocked at C? Well, it means that it's somewhere in this crescent moon region, inside circle A and outside circle C. Now, experiments tell us that a full 50 of these 100 photons that pass through A should get blocked at C. But if we take into account how these photons would behave if B was there, that actually seems impossible. Either those photons would have passed through B, meaning they're somewhere in this region here that we talked about earlier of passing both A and B but getting blocked at C, and that includes fewer than 15 photons. Or they would have been blocked at B, which puts them in a subset of this other crescent moon region that represents those passing A and getting blocked at B, and that guy has 15 photons. So the number passing A and getting blocked at C should be strictly smaller than 15 plus 15. But at the same time it's supposed to be 50? I mean, how does that work? Remember, that number 50 is coming from the case where the photon was just never measured at B. And all we're doing here is asking what would have happened if it was measured at B, assuming that it has some kind of definite state even when we don't make that measurement. And this is what gives us a numerical contradiction. For comparison, think of any other non-quantum questions that you might ask. Like, take 100 people and ask them if they like minute physics, if they have a beard, and if they wear glasses. Well, obviously everyone likes minute physics, but then among those, take the number that don't have a beard, plus the number who do have a beard but not glasses. Now that should be greater than or equal to the number who don't have glasses. One is just a superset of the other. But as absurdly reasonable as this is, some questions about quantum states seem to violate that inequality, which contradicts the premise that these questions could have definite answers, even when the measurements are not made, right?
Well, unfortunately there's a hole in that argument. Drawing those Venn diagrams assumes that the answer to each question is static and unchanging. But what if the act of passing through one filter changes how the photon will later interact with other filters? Then you could easily explain the results of the experiment. So we haven't proved hidden variable theories are impossible, just that any hidden variable theory would have to have the interaction between the particle and one filter affect the interaction of the particle with other filters. We can, however, rig up an experiment where the interactions cannot affect each other without faster than light communication, but where the same impossible numerical weirdness persists. The key is to make photons pass not through filters at different points in time, but at different points in space at the same time. And for this, you need entanglement. For this video, what we'll mean when we say two photons are entangled is that if you were to pass each one of them through filters oriented the same way, either both pass through or both get blocked. That is, they behave the same way when measured along the same axis. And this correlated behavior persists no matter how far away the photons and filters are from each other, even if there's no way for one photon to influence the other. Unless somehow it did so faster than the speed of light. But that would be crazy.
So now here's what you do for the entangled version of our photon filter experiment. Instead of sending one photon through multiple polarizing filters, you'll send entangled pairs of photons to two faraway locations and simultaneously, at each one of those locations, randomly choose a filter to put in the path of the photon. Doing this many times, you'll collect a lot of data about how often both photons in an entangled pair pass through the different combinations of filters.
But the thing is, you still see all the same numbers as before. When you use filter A at one site and filter B at the other, among all those photons that pass through filter A, about 15% have an entangled partner that gets blocked at B. Likewise, if they're set to B and C, about 15% of those that do pass through B have an entangled partner that gets blocked by C. And with settings A and C, half of those that get through A get blocked at C.
Again, if you think carefully about these numbers, they seem to contradict the idea that there can be some hidden variable determining the photon states. Here, draw the same Venn diagrams that we had before, which is to assume that each photon actually does have some definite answers to the questions: would it pass through A, would it pass through B, and would it pass through C? If, as Henry said, 15% of those that pass through A get blocked at B, we should nudge these circles a bit so that only 15% of the area of this circle A is outside circle B. Likewise, based on the data from entangled pairs measured at B and C, only 15% of the photons passing through B would get blocked at C. So this region here inside B and outside C needs to be sufficiently small. But that really limits the number of photons that would pass through A and get blocked by C. Why? Well, look, this region representing photons passing A and blocked at C is entirely contained inside the previous two. And yet, what quantum mechanics predicts, and what these entanglement experiments verify, is that a full 50% of those measured to pass through A should have an entangled partner getting blocked at C. If you assume that all these circles have the same size, which means any previously unmeasured photon has no preference for one of these filters over the others, there is literally no way to accurately represent all three of these proportions in a diagram like this. So it's not looking good for hidden variable theories.
So again, for a hidden variable theory to survive, these results can only be explained if the photons are able to influence each other based on which filters they pass through. But now we have a much stronger result, because in the case of entangled photons, this influence would have to be faster than light. The assumption that there is some deeper underlying state to a particle, even if it's not being probed, is called realism. And the assumption that faster than light influence is not possible is called locality. What this experiment shows is that either realism is not how the universe works, or locality is not how the universe works, or some combination, whatever that means. Specifically, it's not that quantum entanglement appears to violate realism or the speed of light while actually being locally real at some underlying level. The contradictions in this experiment show it can't be locally real, period.
What we've described here is one example of what's called a Bell inequality. It's a simple counting relationship that must be obeyed by any set of questions with definite answers, but which quantum states seem to disobey. In fact, the math of quantum theory predicts that entangled quantum states should violate Bell inequalities in exactly this way. John Bell originally put out the inequalities and the observation that quantum mechanics would violate them in 1964.
Since then, numerous experiments have put it into practice, but it turns out it's quite difficult to get all your entangled particles and detectors to behave just right, which can mean observed violations of this inequality might end up with certain loopholes that might leave room for locality and realism to both be true. But the first loophole-free test happened in 2015.
There have also been numerous theoretical developments in the intervening years, strengthening Bell's and other similar results. That is, strengthening the case against local realism.
In the end, here's what I find crazy. Bell's theorem is an incredibly deep result, upending what we know about how our universe works, that humanity has only just recently come to know. And yet the math at its heart is a simple counting argument, and the underlying physical principles can be seen in action with a cheap home demo. It's frankly surprising more people don't know about it. Thank you so much for watching, and thank you again to Grant for doing this collaboration. This is a topic that I've wanted to do for ages and would not have gotten around to it were it not for doing this with Grant. You know, it's a longer video and his style makes makes perfect sense for doing something like that.
Like, thank you for letting me part of this. Like, this is definitely something outside of my wheelhouse I wouldn't usually have done.
So definitely go check out Grant's channel, 3 Blue 1 Brown, and in particular check out the second video that goes along with this one. It's about kind of fundamental math of quantum mechanics.
I mean, we just kind of want to show how the math of waves is kind of the same thing as the math of quantum mechanics, so check it out. I hope you like it. I was just going to ask you, Henry, like, what aspects of this project went differently from what you might have expected when we first started talking about it?
I think it took longer than I expected. Projects always take longer than you expect.
I use Febreze Fabric Refresher every day to make my home smell amazing. On my bed, my couch, my jacket or jeans, in between washes, even shoes. Febreze doesn't cover up odors with scent, but fights them and freshens. Over 1,000 uses. Febreze Fabric Refresher.
Can I hold it?
Only if you promise to be really, really careful.
I promise I will be so incredibly careful. I will be incredibly careful with it.
Okay.
I promise.
All right. So, it's slippery, be careful.
All right. Are you ready? I'm about to touch a 1 kilogram sphere of silicon-28 atoms. There are about 2.15 times 10 to the 25 of them. Oh. It feels absolutely incredible. Wow, that is amazing. Besides its creators, I am one of only a handful of people ever to hold this sphere. The raw material used to make it was worth 1 million euros, but now that it has been so precisely sculpted, how much is that worth?
It's priceless. This you're looking at now is the roundest object in the world.
How can you say for sure that it's the roundest object? I mean, the Earth is pretty round, isn't it?
If this was the Earth,
if this were the Earth, then the highest mountain and the lowest valley would be
about 14 meters apart.
That is shocking. That is shockingly round. But why would you invest 1 million euros and thousands of man-hours perfecting a pure, polished silicon sphere? Well, the answer is grave. Or rather, grave, as it would have been pronounced in the original French. You see, the grave was the original name for the base unit of mass in the metric system, which became the System International d'Unité, or SI units. In 1793, a commission, which included notable scientist and aristocrat Antoine Lavoisier, defined the base unit of mass as the weight of a cubic decimeter of water at the melting temperature of ice. Essentially, just a liter of ice water. The name grave came from the Latin gravitas, meaning weight, but it wasn't to last. It sounded too similar to the aristocratic title Graf, which is the equivalent of an earl or a count. And with the French Revolution in full swing, with the rallying cry of equality for all, you couldn't exactly have one unit nobler than the others. At this, Lavoisier lost his head, literally. Not because he helped devise one of the greatest systems of measurement of all time, but because he was collecting taxes as a nobleman. So things really were grave. The new Republican government believed a grave would be too big for the things they wanted to measure anyway, and so they settled on a gram, which was just 1,000th of a grave. But soon they realized that a gram was too small, and so they returned to the grave. But since they couldn't call it that, they invented the kilogram, 1,000 grams. And that is why, out of the 7 base SI units, the kilogram is the only one to have a prefix in its name. In 1799, the kilogram definition was refined to be the mass of a liter of water at 4 degrees Celsius, the temperature at which it is densest. But water itself is obviously not the most sensible thing to use as a mass standard. So a pure platinum cylinder was created to have the same mass as the water definition, and it was declared kilogram of the archives. Now it's important to note at this point, the kilogram is no longer tied to the mass of a volume of water. The kilogram of the archives is, by definition, the kilogram. 90 years later, in 1889, the kilogram was upgraded to a platinum iridium alloy cylinder. Now, it was much harder than the original, but was otherwise basically identical. And to this day, it remains the definition of the kilogram. It is officially called the International Prototype Kilogram, though it's affectionately known as Le Grand K, or Big K. Oh, and it's about this big. It is the only thing in the entire universe with a mass of exactly 1 kilogram, because it is the kilogram. It is also the only SI unit that is still defined by a physical object. It sits under 3 bell jars next to 6 sister kilograms in a climate-controlled vault locked by 3 independently controlled keys in the basement of the International Bureau of Weights and Measures on the outskirts of Paris. Now, if you were able to break into the vault and tamper with Big K, you would actually be changing the definition of the kilogram, a definition on which many of our measurements rely. And so you would throw the world into chaos. Well, no, not actually. But how would anyone ever know if the mass of Big K changed? Well, when it was first created, 40 identical replicas were also made. Well, they weren't quite identical. They had a mass which was slightly different to Big K, but those offsets were recorded. Now, these replicas were sent out to countries around the world to serve as their national standards. In 1948, the kilograms were reunited for a weigh-in, and this is when the problems started. Because even though all the cylinders were made of the same alloy and stored under virtually the same conditions,
they say it took 6 days to make the Earth. How did they know it was 6?
their masses had diverged over time. The mass of Big K wasn't even the same as the 6 sister cylinders stored with it. And to make matters worse, when they were brought together again 40 years later, their masses had further diverged, up to about 50 micrograms. That's about the weight of a fingerprint. But fingerprints were not the culprits, since the kilograms were carefully washed before their weigh-ins. So some physical process must have actually changed the mass of the cylinders. But how that exactly works remains a matter of speculation. One thing is for certain, the mass of a platinum iridium cylinder is not stable over time. And this is a big problem. You can't have a unit which changes its value. And the fallout isn't limited to measurements of mass, since of the 7 base SI units, 4 of them depend on the mass of the kilogram, not to mention all the derived units like newtons, joules, volts, and watts. At this point, those of you in countries that have not adopted the metric system, yes, I'm speaking to you, Liberia, Burma, and the US, you may be feeling rather smug that your base unit of mass, the avoirdupois pound, is no longer defined by a physical object. No, instead, it is defined as precisely 0.45359237 kilograms sucked in. So clearly, something needs to be done to eliminate the kilogram's dependence on a physical object. And this is where the silicon sphere comes in. But how exactly does that help? Here you have a physical object, and it's beautiful, but, it's still a physical object. You're trying to get away from that.
We're trying to get away from the physical object, but what we're doing with this particular object is counting how many atoms are in there.
You can't actually count how many are in there, can you?
You can't count how many are in there, but you can calculate how many are in there because this material is silicon. There's no voids or dislocations.
So this is like a perfect crystal of silicon.
That's right.
Not only is it pure silicon, it contains only one isotope of silicon, silicon-28. And that explains why the original material was so expensive. And why a sphere?
Well, a sphere is a pretty simple object. If you know the diameter of the sphere, you can characterize the entire dimension of the object.
Well, that explains why the sphere has to be the roundest object ever created. But how do you actually make something that round?
We actually start with an oversized sphere. So it was about 2 millimeters larger in diameter. And then we just grind it progressively finer and finer using abrasive. It's actually massaging atoms. You're down at that level of trying to control the shape of an object down at the atomic level.
But making the sphere is only half the battle. Then you need to accurately measure its diameter.
The diameter is actually measured via a laser. So you're actually measuring having the sphere in the center of a cavity, and a laser is hitting both sides, and you're actually measuring the gap.
By knowing the diameter, you can determine its volume, and since the atom spacing of silicon is known to high precision, you can then calculate how many atoms make up the sphere. This allows you to redefine Avogadro's constant. At the moment, Avogadro's constant is defined based on the kilogram. It is equal to the number of atoms in 12 grams of carbon-12. But using this approach, the number of silicon atoms in the sphere would be used to fix Avogadro's constant, which would then define the kilogram. So even if the silicon spheres were lost or damaged, it would have no effect on the definition of the kilogram, because it would be defined not by a physical object, but by a concept. If you would like to see the official definition of the kilogram, say, a kilogram is the mass of 2.15 times 10 to the 25 silicon 28 atoms.
Yes.
Is it going to happen?
There's a likelihood, a high likelihood that it's going to happen.
But there is another approach to redefining the kilogram, which involves fixing Planck's constant, and it's done using something called a Watt balance. These two approaches are complementary. Each one provides a check on the other. And if they show good agreement and are able to bring their uncertainties down to about 20 micrograms, they may redefine the kilogram as early as 2014. And then the kilogram finally will be an unchanging unit, no longer defined by a physical object in the basement vault of some place in Paris. Now, if the kilogram was originally intended to be the mass of a liter of water at its densest temperature, then how well did we do? Well, if you look at a liter of water at nearly 4 degrees Celsius, it has a mass of 999.975 grams. So I guess you could look at this two ways. On the one hand, you could say the kilogram is slightly heavier than it should be. But on the other hand, 214 years ago, scientists were able to create an artifact that was correct within the margin of error of a grain of rice. Now that is truly remarkable. Now if you want to hear more about the Watt balance, let me know in the comments and I will see what I can do. It does seem to be the front runner in terms of redefining the kilogram. So we will have to wait and see what happens. One last thing, I should point out that it took an international collaboration of scientists to create the silicon sphere. But don't you think that the scientist who originally conceived of silicon as an element should receive some of the credit? Well, in 1787, that was none other than Antoine Lavoisier. So he's been involved in the definition of a kilogram from start to finish, or from cradle to grave.
You can have a dog like flying into space, or an astronaut cod, or whatever you want.
Let's do all the
So I'm not it's overloaded.
Radiation is frightening. At least certain types of it are. I mean, my Geiger counter doesn't go off near my mobile phone or the Wi-Fi router or my microwave. That's because a Geiger counter only measures ionizing radiation. That is, radiation with enough energy to rip electrons off atoms. And it's measured in units called sieverts. If you're exposed to more than 2 sieverts all at once, you'll probably die shortly after that. But we're exposed to low levels of ionizing radiation all the time. Bananas, for example, are rich in potassium, and some of that potassium is naturally radioactive. So when you eat a banana, you're actually exposed to about 0.1 microsieverts of radiation. That's 1/10,000,000th of a sievert. Let's use a banana for scale of radiation doses. You know, since people eat bananas, we become radioactive too. So you're actually exposed to more radiation if you sleep next to someone than if you sleep alone. But I wouldn't worry about that, because that dose is insignificant compared to the natural background radiation of Earth. mean, there's ionizing radiation coming out of the soil and the rocks and the air and even from space. The level of radiation here in Sydney is about 0.15 microsieverts per hour. And that's about average globally. The level's usually between 0.1 and 0.2 microsieverts per hour. But there are places with significantly higher levels. So who on Earth do you think receives the maximum dose of ionizing radiation? Let's answer that question by going to the most radioactive places on Earth. Some places you'd expect to have high levels of radiation might surprise you. I'm in Hiroshima, and that is the Peace Dome. It was about 600 meters above that dome where the world's first nuclear bomb was detonated over a city. It was detonated there to have maximum destructive impact. With a level of radiation today, almost 70 years later, is only 0.3 microsieverts per hour. I'm about to get into an elevator. We're going down the mine shaft. This is an old uranium mine. This is the mine where uranium was discovered. It's also the place where Marie Curie obtained her raw material. 1.7 microsieverts per hour. It's about 10 times the natural background that you would have. Nowadays, most of the uranium has been removed. But in this wall, there's still a small piece, and you can see under UV light, it fluoresces. Look at that. Fluorescent uranium ore. This is the lab of Marie Curie. She won 2 Nobel Prizes, one in physics and one in chemistry. And she conducted a lot of her work here. And this is her office. She would have sat right there. Apparently there are only a few parts of this area which are still radioactive. One is this doorknob.
Well, it climbs not much, but...
But that's like 10 times the background.
Yes. More than 10.
And another is the back of her chair. You can still detect alpha particles coming off this spot right here. Apparently after she was working in the lab, she would come, open the door, leaving traces of radium here, and then go and pull out her chair. Welcome to New Mexico. This is the Trinity Bomb Test Site, where the world's first nuclear bomb was set off. Right here, right in this spot. This whole area was vaporized. In fact, there was so much heat liberated by that bomb that it fused all of the desert sand into this green glass. And you can still find it here. They've actually named this mineral after the test. It's called trinitite. Yeah, this is the only place on Earth that this has ever been made. The level of radiation here is about 0.8 microsieverts an hour. The trinitite itself is a little bit more radioactive. I got readings of 2 or 3 microsieverts an hour off them. Now, which place has higher levels of radiation than anywhere we've seen so far? The answer is an airplane. You know, as you gain altitude, there's less atmosphere above you to shield you from cosmic rays. So the level of radiation inside the plane can go up to 0.5 microsieverts per hour at 18,000 feet, up to 1 microsievert per hour at 23,000 feet, over 2 microsieverts per hour at 33,000 feet, and over 3 microsieverts per hour at even higher altitudes and towards the poles. That is Chernobyl nuclear reactor number 4. It melted down on April 26, 1986. So what happened was so much heat was generated inside that reactor that it basically blew the top off, spreading radioactive isotopes throughout this whole surrounding area and over into Europe. And that is why we can still detect the contamination here today. Now right now it's reading around 5 microsieverts an hour. If I stayed here for 1 hour, my body would receive a similar dose to what you'd receive when you get a dental x-ray. So this is not a huge amount of radiation. And one of the reasons why the radiation level is not too high is because they actually removed a couple meters worth of topsoil from this whole area. Then they dumped it somewhere. That's why we can stand here.
Caramel In a Reese's? Okay, I have a few questions. Oh, cool. That clears it up. Thanks.
We're driving into the Fukushima exclusion zone now. I'm just watching as the levels on my Geiger counter go up as we approach the zone. See those black bags at the side of the road? The Japanese are doing now exactly what the people in Chernobyl did, collecting up meters and meters of topsoil. The mask is probably overkill. It's just to stop radioactive dust from getting into my lungs. This is definitely one of the most radioactive places where I've been. Even though the release of radioactive material was less than Chernobyl, only about 10%. Because it's much fresher, only 3 years since the accident, much less of it has decayed. So I've been getting readings up around 5 to 10 microsieverts an hour. And I think we won't be staying here for too long because of that. I'm about to go into the hospital at Pripyat, and this is where the firemen were taken after they fought the fires at the Chernobyl reactor. And in the basement of this building, they have left all of the firemen's clothing. Once they realized it was so contaminated, they chucked it down there.
That shoe? 80.
But you can see there's a huge pile of that gear there.
Right outside the door, I'm getting 500 microsieverts an hour just outside the door. 1,500 microsieverts an hour. You know, if we stayed here for a couple hours, we'd receive our annual dose of background radiation.
That basement was the most radioactive place I visited, and it's one of the most radioactive places on Earth. If I'd stayed down there for 1 hour, I would have received 2,000 microsieverts. That's a year's worth of natural background radiation. Every yellow pixel here represents a banana. Now that might seem like a lot, but consider that in a CT scan, the patient receives about 7,000 microsieverts. That's 3 years worth of natural background radiation. It's been estimated that the people living around Fukushima will receive an additional 10,000 microsieverts over their lifetime due to the nuclear power disaster. For comparison, US radiation workers are limited to a maximum of 50,000 microsieverts per year. But that's less than another occupation, astronaut. An astronaut on the space station for 6 months will receive about 80,000 microsieverts worth of radiation. But not even they are exposed to the highest levels of ionizing radiation. So can you guess who is? The answer is a smoker's lungs. A smoker's lungs on average receive 160,000 microsieverts worth of radiation every year. That's due to the radioactive polonium and radioactive lead in the tobacco that they're smoking. So not only are they exposed to carcinogens and toxins, they also receive very high levels of radiation. So it's not the people of Fukushima or Chernobyl or radiation workers or even astronauts who receive the highest doses of ionizing radiation. That honor goes to your ordinary, average smoker. Hey, as you can see, over the last few months I've been traveling around the world actually filming a documentary for television. It should be on in the middle of next year. But being in places like Chernobyl and Fukushima reminded me of this book, The Day of the Triffids. It's about a post-apocalyptic world in which plants take over. I know it sounds like a crazy idea, but it's actually a brilliant book, so you should really check it out if you're looking for something to do over the holidays. Now, you can download this book for free by going to audible.com/Veritasium, or you can pick any other book of your choosing for a 1-month free trial. Audible is a great audiobook website with over 150,000 titles in all areas of literature, including fiction, nonfiction, and periodicals. So I really want to thank Audible for supporting me, and I want to thank you for watching.
Febreze. Hi,
I use Febreze Fade Defy Plug.
And I use this.
Febreze has a microchip to control scent release, so it smells first day fresh for 50 days.
50 days?
And its refill reminder light means I'll never miss a day of freshness. Febreze Plug.
I have a friend named Sammy who, back in the early 2000s, wrote some code for his MySpace page. And what the code did was anyone who visited his page would have his picture and the tagline that said, "Sammy is my hero," copied over to their homepage. And that was a bit of fun for a while, but Sammy wanted more. And so he tweaked his code so that not only the picture and the tagline were copied over, but also the code itself. And now it exploded. In just 9 hours, he had reached 480 accounts. In 13 hours, he was up to 8,800. And in just over 18 hours, he had hit 1 million accounts, which was a full 1/35 of all the accounts on MySpace at the time. So in a panic, he tried to delete his page. And when he was successful, he actually took down the whole of MySpace with it. He was arrested and convicted of computer hacking and ordered not to touch a computer for the next 3 years. But I think what this story really tells us is just how connected we all are. Imagine you have 44 friends, and each one of those friends has 44 friends who are not also your friends. And each of them has an additional 44 friends, each of whom has 44 friends, who again has 44 friends, and they have 44 more. Then, in a chain of just 6 steps, you would be connected to 44 to the 6, or 7.26 billion people, more than are alive on Earth today. And we've contemplated how closely connected we are since long before MySpace even existed. Back in 1929, a Hungarian author and poet named Frigyes Karinthy wrote a short story called Chains. And in it, one of the characters challenges the others to find another person on Earth that he cannot connect himself to through fewer than 5 intermediaries. This is the origin of 6 degrees of separation. If the theory is correct, it means that you would be connected to the Queen or Tom Cruise in just 6 steps. But they may be the easy ones. What about this shop owner or the Mongolian sheep herder? What the theory really means is that any 2 people picked at random from anywhere on the Earth will be connected by just 6 steps. The idea remained just fiction until in the 1960s, a Harvard psychologist, Stanley Milgram, attempted to test it. He called it the small world experiment, after that phenomenon where you're at a party, you meet a stranger, and you find out that you have a friend in common. And you remark, "Oh, it's such a small world." What he did was he sent out 300 packages to people both in Boston and in Nebraska. Now, what he wanted those people to do was try to send their package to a target person in Boston. But they weren't allowed to send it directly to him. They had to send it to someone they knew on a first-name basis, who they thought had a better chance of knowing the target, and they could forward it on in the same way. Now, as you might expect, most of the packages never made it, but 64 did, and the average path length was 5.2. So now 6 degrees of separation had experimental confirmation. Or did it? If you look more closely at Milgram's sample, you find that of the 300 people, 100 were located in Boston, the actual city where the target lived. Another 100 were stockbrokers, which was the same profession as the target. So only 100 people lived in a different state and had a different job. And of them, only 18 of their packages made it to the target. So we're talking about a sample size of 18 is all the evidence there was for 6 degrees of separation. So experimental evidence was tough to come by. But a decade earlier, a mathematician named Paul Erdos had tried to work out the theoretical properties of networks like these. But he didn't have any information on the structure of real social networks, so he decided to work on networks where the connections between nodes were all completely random. And we can actually simulate a network like this using buttons and thread, where we just connect up the buttons at random. What Erdos found is that when the number of links per node is small, the network is fragmented. Pick up any button and few others will come with it. But once you exceed an average of 1 connection per node, the behavior of the network changes dramatically. They almost all link up, forming a giant cluster. Now if you pick up any button, almost all of the rest will come with it. This change happens rapidly, and it resembles a phase transition in physics. And you could call this a small world network, since the path between any 2 buttons is short. The thing about random networks is that they are naturally small world networks, because you're just as likely to be connected to someone here in Manila as you are to someone in your own town. But obviously, a random network doesn't represent real life very well. So what do real-world networks look like? Well, for that, we need to go to the empirical data. In 1994, a couple of college kids invented a game called 6 Degrees of Kevin Bacon, in which you try to connect any actor to Kevin Bacon through just 6 steps, through his co-stars. Now, a couple of sociology researchers got access to their database of 250,000 actors, and they analyzed the network, and what they found was that it was a small world network, meaning between any 2 actors, there were only a very small number of steps. And that's very similar to a random network. But unlike a random network, the actor network also showed a high degree of clustering. That is, they often work together in small groups. So how do you get both this grouping behavior, a high degree of clustering, and the short number of steps between any 2 actors? Well, to figure this out, they looked at 2 different extremes. Imagine a circle of nodes. Now, if you connect them at random, you get the same outcome as Erdos. Short paths between any 2 nodes, but little clustering. Now consider connecting up the nodes only with their nearest 2 neighbors on each side. Now clustering is high, but path lengths are long for 2 nodes picked at random. But what if you take this setup and rewire just a small number of connections randomly? What you find is that the path length drops rapidly, but clustering still remains high. So the key to modeling real social networks is to have a lot of clustering behavior, that is, your friends are also friends with each other, but also to have a few random acquaintances. And the importance of those acquaintances can't be overstated. There was a researcher named Granovetter in the 1970s who published a paper called The Strength of Weak Ties, in which he points out you are much more likely to get a job through those random acquaintances than through your close friends. And if you think about it, that makes sense, because you and your close friends all know the same people and have the same information. It's through the random acquaintances that you can get connections with people very far from your social circle, so you can find new jobs, new places to live, and you can be connected to the outside world. So in fact, it is those random acquaintances that make possible 6 degrees of separation.
So I'm told the degrees have dropped in recent years.
Really?
To like 4 degrees.
Tell me about that. How do we know this?
I don't know how they measure it, but I've tested it, and I think it actually has dropped based on how many people have friended one another on Facebook. The friendship circles have grown. Not that they're bosom buddies, but they're people you have access to. That's the point.
Right.
And it's, do you know this person who then knows that, so that I have access to these other people? So I'm told that it has dropped. Okay. It's not just the 6 degrees. We're down at 4, at most 5.
I think Neil deGrasse Tyson might be right. In 2011, Facebook analyzed their data, and they found that 92% of their users were connected through just 5 steps, and that number is decreasing over time. The concept of 6 degrees of separation has fascinated people for nearly a century, and I think that's not only because of how counterintuitive it is, but also how comforting it is to know how closely we are all linked. Not in some kind of abstract, ill-defined way, but through hard scientific data. Just 6 handshakes will connect you to anyone else on the planet. Now I have a challenge for you. In the spirit of 6 degrees of separation, I want to try an experiment. I want you to try to get an email to me, but you can't send it directly to me unless you know me. So assuming you don't, I want you to send it to a friend of yours, someone you know on a first-name basis who you think has a better chance of getting that email to me. If your email eventually gets to me through a chain of people, I will send you a postcard in the mail, and I'll tally up if we were able to get that done in 6 links or not. So let's try to do it and see if we can connect. The instructions are in the description. This episode of Veritasium was inspired by the Fine brothers, Ben and Raffi Fine, who are friends of mine, so we are connected through just 1 degree of separation. Now they have a brand new TV series launching on truTV. It's called The 6 Degrees of Everything, and it's a fast-paced comedic show that tries to show us how 6 things that we don't think are connected actually are. It involves sketch comedy and songs and reality TV. I'm really looking forward to seeing how they are going to do this. So you can check it out Tuesdays at 9:30 or 8:30 Central on truTV. I am so looking forward to it. And thank you to the Fine brothers for sponsoring this episode so I could check out the science of networks.
Mitsubishi Motors delivers confidence every day with their new integrated care program. 2 years of included maintenance, an industry-leading warranty, and its standard.
Most processes in our universe are time reversible. In other words, the physics works the same way forwards or backwards, which is why you can't tell if I'm playing these videos normally or in reverse. People typically point to entropy as the only exception to this rule. The second law of thermodynamics states that the entropy of a system, or the amount of disorder, always increases with time. But increasing entropy is an emergent property, the result of the motions of many, many particles, which raises the question, can fundamental particles themselves tell the direction of time? Or in other words, is there a physical process on the scale of individual particles that looks different forwards versus backwards? The answer, surprisingly, is yes. In particle physics, there are 3 major symmetries that we're always expected to hold: charge, parity, and time. Time symmetry, as we've already discussed, means interactions work the same way forwards or backwards in time. Charge symmetry means interactions are unaffected if all the charges are swapped. In other words, there is nothing special about what we call positive charge. Nature treats it exactly equal and opposite to negative charge. And parity symmetry means the laws of physics are indifferent to left or right-handedness. Now, to understand what that means, imagine a giant mirror were held up to our universe. And in the mirror, the z direction is reversed, and my right hand becomes my left hand. But the laws of physics shouldn't care. I mean, they should work exactly the same way in the mirror world as they do in the regular one, with no preference for left or right-handedness. Or to put it another way, there should be no experiment that you could do that would tell you whether or not you are in the mirror world. Each of these symmetries is known by its initials, C, P, and T. In the 1950s, it was thought that all fundamental particles obey these symmetries. But then in 1956, a paper written by Li and Yang pointed out that parity symmetry had actually never been tested in experiments involving the weak force. So at Christmas break that year, physics professor Xian-Xiang Wu of Columbia University had planned to go on vacation with her husband, who was also a physicist, but instead, so intrigued by the possibility that the weak force might violate parity, she decided to stay behind and be the first person to test it. To do this, she and a team of low-temperature scientists cooled a collection of cobalt-60 atoms to just 3,000th of a degree above absolute zero. Then they applied a strong magnetic field to align all the nuclei with their spin pointing in the same direction. Now, cobalt-60 is radioactive, and it decays via the weak nuclear force, releasing a beta particle, which is just an electron. And what the experiment measured was the direction in which these electrons were emitted relative to the spin of the cobalt-60 nuclei. To see how this would work under parity symmetry, let's consider the mirror image version of this experiment. In the mirror, the direction of the z-axis is flipped, but the direction of nuclear spin is not. That's because an object that's rotating clockwise is still rotating clockwise in the mirror. So, this means that the spins of the regular and mirror nuclei are aligned. The mirror experiment is actually the same experiment as the original. Now, when a cobalt-60 nucleus decays and emits an electron, that electron could go, say, to the left or to the right. Now, if parity symmetry is respected, the electron should be equally likely to go in any direction. That way, both the normal and mirror image experiments would give the same results. However, if the electrons were emitted in one direction preferentially, say in the positive z direction, well then in the mirror experiment, the electrons would also have to fly off preferentially in the mirror positive z direction, which is opposite to the original positive z direction. So in the normal experiment, the electrons would be emitted, say, opposite the direction of nuclear spin, but in the mirror version, they'd be emitted in the same direction as nuclear spin. So how does this make any sense? It would allow you to determine whether you're in the mirror world or not. It's like the spinning top from Inception. If the electrons from the cobalt-60 nuclei go one way, you're in mirror world, and if they go the other way, you know you're in normal world. Now, crazy as this may seem, this is exactly what Professor Wu saw. Electrons were emitted preferentially in one direction, and not just by a little bit. They were predominantly emitted opposite nuclear spin. So not only does the weak force violate parity, it comes close to violating parity as much as is physically possible. This destroyed a basic assumption of theoretical physics that had been around for decades. Somehow the universe cares about left or right-handedness. When Wu announced her results, they shocked the physics world. After being told of the experiment, famous physicist and Nobel laureate Wolfgang Pauli said, "That's total nonsense," and insisted the result was mistaken. When the experiment was independently replicated, theoretical physicists had to accept that the universe we live in is not the one they had imagined. The Nobel Prize was actually awarded for the discovery of parity violation in 1957, the very same year these results were published. This required a profound shift in thinking for physicists, but before throwing everything out and starting again from scratch, they formulated a workaround. Maybe it was okay that the weak force broke parity, because it's not a real symmetry of the universe itself, just part of a larger symmetry, charge parity, or CP symmetry. The idea was if the mirror flipped not only these axes, but it also swapped the particles for antiparticles with their charges reversed, well, then the symmetry would be restored, and the mathematics behind our laws of physics would still work. Now, this gave physicists some comfort, until in 1964 it was found that some particles can also violate the combined charge parity symmetry. And boom, you got yourself another Nobel Prize. Now, two rules which physicists once thought were fundamental laws of nature were broken. So they retreated behind their last set of theoretical defenses, the combined symmetry of CPT, where T is time. Sure, they said, the weak force violates parity and charge parity, but certainly not charge parity and time together. And to this day, physicists are still pretty sure that CPT is a real symmetry of the universe. So far, no experiment has found a violation of CPT. In fact, if CPT is violated, we would have to rewrite a lot of the last century's work, because it would mean that special relativity and quantum field theory are both wrong. Okay, so let's say that CPT is a true symmetry. Think about the implications of this. If we know that CP can be violated, but CPT cannot, then time symmetry must also be broken. Otherwise, there would be no way for the combined three-way symmetry to be maintained while two of the subsymmetries are broken. And physicists have actually conducted experiments that confirm that certain particles directly break time symmetry. For example, when a pair of quarks are held together by the strong force, there are sometimes two different possible arrangements, and they can switch back and forth between these two arrangements via the weak force. But switching in one direction takes longer than switching back. So if you could make a recording of this event, it would look different if you played the recording forwards than if you played it backwards. And that's exactly what it means to break time symmetry. In certain cases, then, fundamental particles can tell the difference between going forwards and backwards in time. The second law of thermodynamics is not the only physical process that prefers one direction in time. Now, is this the origin of our perception that time only goes one way? Or is it the reason for the universe's arrow of time? The truth is that we still have no idea why time only goes in one direction. What's interesting is that physicists once thought that parity, charge, and time were these symmetries that were unbreakable. But over time, each of these symmetries was demonstrably violated. So is the ultimate symmetry, CPT, also unbreakable? Or will it fall, taking quantum field theory and special relativity with it? These are just some of the big, basic, unresolved mysteries left in our quest to understand the universe. Perhaps one day, another physicist will give up their vacation to figure out the answer. This episode of Veritasium was animated and co-written by my friend Jorge Cham, who is also the creator of PhD Comics, and now he's written a book.
Yeah, it's called We Have No Idea. It's a book I wrote with physicist Daniel Whiteson, and it's about all the things we don't know about the universe. All of the big things like dark matter and dark energy, but also all the little things like what are all those fundamental particles for?
And it has cartoons in it.
Yep, and lots of bad puns.
So if that sounds like it's up your alley, you should check it out. I'll put a link to it in the description and all of Jorge's other projects.
Thanks.
For most of us, thinking is at least somewhat unpleasant. We try to avoid it where possible. For example, I asked these guys, how long does it take for the Earth to go around the sun?
What do you reckon, cuz? Isn't it 24 hours? Obviously a day, yes.
Or take this problem, which has been given to thousands of college students. You go into a toy store, and there's a toy bat and a toy ball. Together they cost $1.10. And the bat costs $1 more than the ball. How much does the ball cost?
10 cents. We're all wrong, aren't we?
If you think about it for just a second, it's obvious that the ball can't cost 10 cents. Because if it did, then the bat would cost $1.10 and the two items together would cost $1.20. The correct answer is 5 cents. Now the point of these questions is not that they're difficult. Any of these people could have quickly checked their answer if they wanted to. The point is that they don't check. Because thinking is uncomfortable. It takes effort.
Hey, the Earth doesn't take one day to get around the sun. It takes like a year.
Now, I think it would be easy to put these mistakes down to stupidity and believe that you, being much smarter, could never fall into such traps. But then I think you'd be fooling yourself. I think these examples reveal blind spots in all of our thinking due to the fundamental way that our brains work. Now, one way of modeling how the brain operates is as though there are two systems at work. Psychologists call them System 1 and System 2, but maybe it's useful to think of them as characters. So let's call System 1 Gun and System 2 Drew. You are Drew. He represents your conscious thought, the voice in your head. I am who you think you are. He's the one capable of following instructions. He can execute a series of steps. If you're asked to calculate 13 times 17 in your head, for example, he's the one who has to do it. Can I just use my calculator? No.
All right. 17 times...
Drew is lazy. It takes effort to get Drew to do anything, and he is slow. But he's the careful one, capable of catching and fixing mistakes.
221.
Now meet System 1, Gun. He is incredibly quick, which he needs to be since he's constantly processing copious amounts of information coming in through your senses. He picks out the relevant bits and discards the rest, which is most of it. And he works automatically, without you, Drew, being consciously aware of what he is doing. For example, when you spot some text, he reads it before you can even decide whether or not you want to read it. Gun fills in the gaps. For example, what does this say? Did you notice that the H in the and the A in cat are actually the same symbol? But you had no trouble reading it because Gun made the correct automatic assumption. So although Drew is unaware of what Gun is doing, it's Gun's perceptions that become the basis for your conscious thoughts. The way I like to think of it, each of these characters is related to one of your main memory structures. Gun's automatic responses are made possible by long-term memory, the library of experiences you've built up over your lifetime. In contrast, Drew exists entirely within working memory, so he's only capable of holding 4 or 5 novel things in mind at a time. This is perhaps one of the best known findings from psychology, that our capacity to hold and manipulate novel information is incredibly limited, like when trying to remember a string of random numbers.
6, 7, 5, 5, 3, 1.
Yes.
But we are able to overcome these limitations if the information is familiar to us. For example, let me give you 4 random digits, 7, 1, 0, 2. Now these would normally take up most of your working memory capacity just to remember, but if you reverse them, 2017, they are now just one thing, the present year. The process of grouping things together according to your prior knowledge is called chunking, and you can actually hold 4 or 5 chunks in working memory at once. So the larger the chunks, the more information you can actively manipulate at one time. Learning is then the process of building more and bigger chunks by storing and further connecting information in long-term memory, essentially passing off tasks from Drew to Gun. But in order for this to happen, Drew first has to engage with the information actively and effortfully, often multiple times. For example, when you were first learning to tie your shoelaces, you probably recited a rhyme to help you remember what to do next, using up all your working memory in the process. But after doing it over and over and over again, it gradually became automatic. That is, Drew doesn't have to think about it anymore because Gun's got it. Musicians and sports stars refer to this as muscle memory, though of course the memory is not in the muscles, it's still in the brain, just controlled by Gun.
You can practice everything exactly as it is and exactly as it's written, but at just such a speed that you have to think about and know exactly where you are and what your fingers are doing and what it feels like.
Slow, deliberate, conscious practice repeated often enough leads to this. I bet 99% of the time what appears to be superhuman ability comes down to the incredible automation skills of Gun, developed through the painstaking, deliberate practice of Drew. What's interesting is it's actually possible to see how hard Drew is working just by looking at someone. Try this task. I'm going to show you 4 digits. I want you to read them out loud, and then after 2 beats, I want you to say each number back on the beat, but adding 1 to each digit. So as an example, 7291 should be 8302. This is called the add 1 task, and it forces Drew to hold these digits in memory while making manipulations to them. Now it's important to say the numbers back on the beat. Try this one.
How do celebrities like Justin Bieber and The Rock generate hundreds of millions of dollars? It's actually not.
To make it harder, you can try adding 3 instead of 1. Ready? Now what you're unaware of is that as you're completing this task, your pupils are dilating. When Drew is hard at work, as he is in this task, you have a physiological response, including increased heart rate, sweat production, and pupil dilation. Watch how the pupils of these participants enlarge as they perform the add 1 and add 3 tasks.
4, 3, 9, 7, 2. 5, 4, 0, 8, 3.
Excellent. Nicely done.
Requires a lot of thinking.
I know. That's the point.
6, 9, 1, 6. 7, 0, 2, 7.
When this research was originally carried out, the researchers made a surprising observation. When the participants were not engaged with the task but were just chatting with the experimenters, their pupils didn't really dilate at all. This indicates that the add 1 and add 3 tasks are particularly strenuous for System 2, and that most of our day-to-day life is a stroll for Drew, with most tasks handled automatically by Gun. Just as we spend a lot of our lives lounging around, our brains spend most of their time doing the mental equivalent. And I don't mean to make that sound like a bad thing. This is how our brains evolved to make the best use of resources. For repetitive tasks, we developed automatic ways of doing things, reserving Drew's limited capacity for things that really need our attention. But in some circumstances, there can be mix-ups. For example, I moved to Australia in 2004, and one of the first things I learned was that to turn the lights on, you flick the switch down. My whole life growing up in Canada, Gun had automated that up means on. So no matter how well I, Drew, knew that down was on in Australia, I would for years continually switch the lights off when entering a room and on when leaving. When Destin learned to ride the backwards bicycle with its steering reversed, it took months to overcome his automated habit. And once he had done that, he couldn't easily go back to riding a normal bike. Understanding Gun and Drew also explains errors in the bat and ball question. It's Gun who first perceives the key pieces of information, that together the bat and ball cost $1.10, the bat costs $1 more than the ball, so the ball costs
10 cents. 10 cents.
Gun immediately had an answer that he blurted out automatically. Meanwhile, Drew, without being consciously aware that the answer came from Gun, endorsed the idea without checking it. After all, the answer sounded reasonable and Drew is lazy. So how do you get Drew to do more work? Well, researchers have found at least one way. When they gave out a clearly printed test, including the bat and ball question to incoming college students, 85% got at least one wrong. But when they printed the test in a hard-to-read font with poor contrast, the error rate dropped to 35%. A harder-to-read test resulted in more correct answers. And the explanation for this is simple. Since Gun can't quickly jump to an answer, he hands off the task to Drew, who then invests the required mental effort to reason his way to the correct answer. When something is confusing, Drew works harder. And when Drew works harder, you're more likely to reach the right answer and remember the experience. This is something I think the advertising industry knows about and is using to its advantage. A few years ago, again in Australia, I saw a giant billboard that had just 2 letters on it. UN. There was no logo, no indication of what it was for, and this seems to go against all the basic principles of advertising, to show what the product does, how it's better than the competition, and use clear branding and maybe a jingle to make it memorable. The goal is usually to make the message as easy to understand as possible, so Drew doesn't have to work very hard. But if you look at a lot of effective advertising today, it's changed to be more confusing. As the UN campaign rolled out across Sydney, I saw ads like this one in bus shelters. Unexplained. With UN, there is no stress, just unstress. No hassle, just unhassle. With UN, you can undo what you did. You can undrive through the car wash with the window down, or unbreakdance in front of your teenage son and his mates, Makes life relaxing and unreal. Your life. Be happy and live for now. Don't worry, unworry. Can you guess what the ads were for? They're actually for insurance. Now that advertising is everywhere, Gun is skilled at filtering it out. It's automatic. If I just saw another insurance ad, I never would have given it a second thought. But something that doesn't make sense? That's something Gun can't deal with, so he hands it off to Drew. This same realization has been happening in education. Lectures, which have long been the dominant teaching method, are now on the decline. Like the old form of advertising, they're too easy to tune out. And often, especially in science lectures, too many new pieces of information are presented, and that exceeds Drew's capacity because he doesn't have big enough chunks to break the material into. In place of lectures, universities are introducing workshops, peer instruction, and formats where students are forced to answer more questions, do more work than just listen and take notes. And this will undoubtedly make Drew work harder, which is good because that's how learning happens. But a lot of students don't like it because it requires more effort. Just as it's hard to motivate someone to get off the couch and exercise, it's hard to get Drew to give his full effort. There's an appeal to doing things you already know, for the musician to play the same familiar songs that Gun has already automated that feel and sound good, to watch videos that give you the sensation of understanding without actually learning anything, to always drive with the GPS on so you never get lost, but you also never learn the way. If you really want to learn and get better at anything, have any chance of becoming an expert, you have to be willing to be uncomfortable. Because thinking takes effort. It involves fighting through confusion, and for most of us, that's at least somewhat unpleasant. Okay, they're about to lock me in here and then use these electric coils to make magnetic fields that rotate. They're roughly the strength of Earth's magnetic field, and we'll see if my brain is picking up on the fact that the magnetic field is changing. The whole time I will have my eyes closed, it'll be pitch black in here, basically no stimuli except for the changing magnetic field, and I'll keep my head perfectly still facing forward. That sound good?
Yep, and it'll take about 8 minutes.
8 minutes, perfect. Okay.
All right.
I'm ready when you are.
But before we do this, let's meet the researchers.
Can you introduce yourself?
Introduce myself. My name is Shin Shimojo. I'm a professor in neuroscience and experimental psychology at here Caltech Biology.
Connie, you are the first author here, and your paper has just been published when this video goes out.
Yes.
So, what is the setup of the paper? How do you set this up?
So basically, we wanted to see if humans have any brain response to a magnetic field.
If you're not making $158,000 per year, but you'd like to, I strongly encourage.
It has long been recognized that certain bird species have a remarkable ability to find their way home, hence the use of homing pigeons to carry messages for us. Their impeccable sense of direction is owed in part to their ability to sense the Earth's magnetic field. But they are not the only animals that do this. Certain bacteria, bees, salmon, turtles,
Rats, dog, whale, cats, all of them are known to have magnetic compass.
dogs, known to poop with their bodies oriented preferentially north-south, have even been trained to locate bar magnets. Given a choice between 3 containers, they were much better than chance at identifying the one containing the magnet. In fact, they were much better at finding a magnet than finding a food treat under similar conditions. Given all these examples, it seems more likely that humans should have the ability to detect magnetic fields. And if you're wondering how humans could physically pick up the magnetic fields, consider that magnetite crystals have been found in the brain that closely resemble those of magnetically active bacteria.
My colleagues in neuroscience said, wow, this is hard to believe, this is impossible. But lots of biologists and geophysicists said, well, it's a matter of course humans are not, exception among all those mammalian species.
But up till now, the evidence has been contradictory and controversial.
So in the early 80s, Robin Baker did some studies where they took groups of students and drove them around in very convoluted routes around the English countryside. and they were blindfolded, and then they would stop the bus and ask the students to identify which direction they came from, to basically home. And they got pretty significant results from that. Shortly afterwards, maybe a few years afterwards, this study was attempted again at Princeton University. And they did just a very similar experiment there, and they couldn't get significant behavioral results there.
There's a controversy, lots of positive reports and failure of duplication, negative data in neuroscience as well. So let's step back and then see if there's any systematic selective response from the brain to the magnetic field itself, not anything associated like vestibular thing or visual scene, swinging and stuff like that.
So this is the test chamber, and I'll turn on the light. Go. So this is our magnetic.
Is that the way we get in?
Yes.
Exactly. That's the way you have to crouch in.
So I'm gonna crawl under there.
Yes. You sit down there.
You want to sit in the chair when you get in.
Hang on a sec. Hang on. This is too cool. I really like it. Whose chair is that?
It just happened to be,
Joe's chair.
Joe's reclining chair, not used for this purpose, but it turned out it's very relaxing. And the main reason of this cage is to shield the outside effect for one thing, and then also have a good control over the modified Faraday cage where electricity is running.
Okay,
and then there's no sound or vision or tactile or any other additional stimulation because we are tapping onto very subtle response of the brain at the subliminal, subconscious level.
It doesn't block the Earth's magnetic field. The Earth's magnetic field goes straight through this. And that's actually sort of what we want, because inside the chamber, we're not trying to override the Earth's field. We're just trying to redirect it, just to add a little bit of field here and here, remove a little bit there. And by doing that, we can smoothly move the field back and forth and move it in a way that relates to how someone might experience the field as they're sort of moving, around outside.
So that's essentially what you're simulating in here.
Yes,
is
correct.
You're making it as though my head is swiveling around in the Earth's magnetic field.
Yes, except that if you're actually doing it in the real world, then your vestibular system is also sending signals. We are not interested in contamination from vestibular signals. So we would like to generate artificially that kind of situation like this. However, eliminating any other sensory modalities such as vestibular.
Can I hop in there and just have a look?
Oh, yes, go ahead.
Okay. I mean, I feel like for my job, I have been in more weird soundproof boxes than most people. These black coils here, do these create the magnetic field?
No. So those are for a different experiment. So the magnet coils are actually these things.
Those are the magnet coils.
And you can see there's 4 of these square coils in all 3 directions. And this is a nested 3-axis coil set. And it's designed to create a magnetic field in any direction inside the chamber. And in the center of the chamber where your head and torso is going to be, it's designed to create a uniform field. So a field with no gradients or curves in it.
I've brought a compass, and so I can just see if the magnetic field is changing. What's going to happen when I sit in this room? Okay, that was a pretty dramatic shift.
So there will be 2 kinds of rotations. One is clockwise and one is counterclockwise. And as a control on some trials, the magnetic field won't change at all. So we can compare on trials what happens after the field rotation versus trials where no field rotated.
So this is the sort of thing that I'll be experiencing, but in the dark.
Yep. Now we're going to want you to use your left hand to hold it here because it's easier to
On the
put
front?
on the cap. Yeah, just hold it.
On this cap, there are 64 electrodes, which will pick up the electrical activity of my brain.
And you're sure this isn't just to make people look stupid?
Oh, no.
When you're awake with your eyes closed, the dominant signal is called the alpha wave. In most people, it occurs around 10 hertz.
These little squiggles right here, they're happening at around 10 times per second. These are the alpha waves.
We are measuring your alpha wave, which is known to be an indicator of relaxing and sometimes even drowsy, but not sleeping. And then when you notice something like in vision or audition or touch, your alpha wave is suppressed. And that is the signature of brain detecting sensory signal and moving attention towards it.
So the goal of this experiment is to determine if a magnetic field rotation causes the amplitude of alpha waves to drop. I'm about to go into the cage.
I'm going to turn off the light, and then we just do this with a stool. Turn off all the lights in the room, and we close the doors. And throughout the experiment, I'll be listening in and watching the video for safety reasons. Can you hear me?
Yes, I can.
I'm setting up the experiment. We'll be starting shortly. Just wait for the ding ding.
Hi, my name's Hannah, and I'm here to show you how students can use Otter to make lectures and campus events more.
The experiment is starting. You can see that's our starting point. In terms of direction, it will vary from 2 preset values. Yep, so you can see there, that was a field rotation. Okay.
This is like one of the more glamorous.
Ah, there we go.
That's what I was not meant to hit. Thank you. Sorry about that.
I could see that happening.
You can see that coming.
Yeah.
And I was thinking about saying something to the camera. I can't wait to see the results though. This is a section of my raw EEG results. You can see that every 3 seconds the field was rotated either clockwise, counterclockwise, or it was fixed, meaning it didn't change. Now, it's impossible to draw conclusions just by looking at this, so the scientists average over all the trials in the different conditions and plot the alpha power over all the electrodes. This is a recording from someone who is particularly sensitive to changes in the magnetic field. As I play this, watch how the clockwise and counterclockwise responses compare to the fixed field result. The recording starts before a rotation. The magnetic stimulus takes place, and now observe the post-stimulus response, particularly for counterclockwise. For this subject, the counterclockwise rotation resulted in a clear decrease in alpha power of at least 3 decibels, shown by the dark blue color. This corresponds to a decrease in alpha power by around 50%. Now, here are my results. After the magnetic stimulus, my response to counterclockwise is clearly not as pronounced. But over time, for clockwise rotations, my alpha power is reduced. I was told I was neither the most sensitive to magnetic fields nor the least sensitive. I was somewhere in the middle.
So the conclusion is that our brains have ability to sense magnetic field change, but it's implicit and subliminal. It's non-conscious part of the brain. This is just the first step to make sure that it's not theoretically impossible that our ancestors might have utilized this ability for their navigation. Even the modern people like ourselves may potentially have it. This will open up the window for the next stage research as to how we could bring it to the consciousness, how could we strengthen them, and how could we utilize it.
As yet, it's unclear if anyone can actually make use of this sense, consciously or subconsciously, to help them navigate. But the study's authors point out that a surprising number of human languages lack terms like front, back, left, and right, and instead use cardinal directions, north, south, east, and west. Native speakers of such languages would refer to a nearby tree as being to their north, rather than being in front of them. Individuals who've been raised from an early age within a linguistic, social, and spatial framework using cardinal reference cues might have made associative links with geomagnetic sensory cues to aid in daily life. In other words, people from such cultures may be conscious of their magnetoreception. They would be very interesting to test. But if it turns out that this sense is no longer functional in humans, just a relic from our ancestors, it would be interesting to consider why we lost it.
Maybe modern world human don't need it. That's one explanation. Another explanation is we are surrounded so much and exposed so much to artificially created strong magnetic fields, starting from the airplane, cabinet, headphone. Some younger people are wearing this for 10 hours per day, including MRI scanner too.
So it's possible our internal compass may be a victim of our modern technology.
This study does not show that magnetic fields have some kind of special influence on you, that they don't cure disease, they don't make you smarter. You can't communicate telepathically or something through them.
So these are the types of emails that Connie does not want to receive. Just so everyone's clear, in case you've got sort of a crazy idea. My hair still looks stupid. In case you have a crazy idea for what to do with magnetic fields in the human brain, this study does not support that.
No, it does not support that. It only supports that the human brain can pick up on the physical stimulus of the Earth's magnetic field. Yup.
Which in itself is a super cool finding.
It is a super cool finding. It's like just the basis for future research, because you can't have any behavior without some kind of something going on in your brain.
Most people have no clue that in 2023, the best way to make money on Amazon is not with physical products. It's Amazon's other company, Audible.
LEDs don't get their color from their plastic covers, and you can see that because here is a transparent LED that also glows the same red color. The color of the light comes from the electronics themselves. The casing just helps us tell different LEDs apart. In 1962, General Electric engineer Nick Holonyak created the first visible LED. It glowed a faint red. A few years after that, engineers at Monsanto created a green LED. But for decades, all we had were those two colors. So LEDs could only be used in things like indicators, calculators, and watches. If only we could make blue, then we could mix red, green, and blue to make white, and every other color, unlocking LEDs for every type of lighting in the world, from light bulbs to phones to computers to TVs to billboards. But blue was almost impossible to make. Throughout the 1960s, every big electronics company in the world, from IBM to GE to Bell Labs, raced to create the blue LED. They knew it would be worth billions. Despite the efforts of thousands of researchers, nothing worked. 10 years after Holonyak's original LED turned into 20, then 30, and the hope of ever using LEDs for light faded away. According to a director at Monsanto, these won't ever replace the kitchen light. They'd only be used in appliances, car dashboards, and stereo sets to see if the stereo was on. This might still be true today, if not for one engineer who defied the entire industry and made 3 radical breakthroughs to create the world's first blue LED. Shuji Nakamura was a researcher at a small Japanese chemical company named Nishia. They had recently expanded into the production of semiconductors to be used in the manufacture of red and green LEDs. But by the late 1980s, the semiconductor division was on its last legs. They were competing against far more established companies in a crowded market, and they were losing. Tensions started to run high. Younger employees begged Nakamura to create new products, while senior workers called his research a waste of money. And at Nishia, money was in short supply. Nakamura's lab mainly consisted of machinery he had scavenged and welded together himself. Phosphorus leaks in his lab created so many explosions that his coworkers had stopped checking in on him. By 1988, Nakamura's supervisors were so disillusioned with his research that they told him to quit. So it was out of desperation that he brought a radical proposal to the company's founder and president, Nobuo Ogawa. The elusive blue LED that the likes of Sony, Toshiba, and Panasonic had all failed at. What if Nishia could be the one to create it? After suffering loss after loss on their semiconductors for more than a decade, Ogawa took a gamble. He devoted 500 million yen, or $3 million, likely around 15% of the company's annual profit, to Nakamura's Moonshot project. Everyone knew that LEDs had the potential to replace light bulbs, because light bulbs, the universal symbol for a bright idea, are actually terrible at making light. They work by running current through a tungsten filament which gets so hot it glows. But most of the electromagnetic radiation comes out as infrared, heat. Only a negligible fraction is visible light. In contrast, LED stands for light-emitting diode. It's right there in the name. LEDs primarily create light, so they're far more efficient. And a diode is just a device with two electrodes, which only allows current to flow in one direction. So here's how an LED works. When you have an isolated atom, each electron in that atom occupies a discrete energy level. You can think of these energy levels like individual seats from a hockey stadium. And all atoms of the same element, when they are far apart from each other, have identical available energy levels. But when you bring multiple atoms together to form a solid, something interesting happens. The outermost electrons now feel the pull not only of their own nucleus, but of all the other nuclei as well. And as a result, their energy levels shift. So instead of being identical, they become a series of closely spaced but separate energy levels, an energy band. The highest energy band with electrons in it is known as the
What up? How's it going, chat? Hello. Hello. What it do, flight crew? How's it going, everybody? I'm sorry. Look, I'm sorry about the delay. There were genuine internet issues. I was here ready to go live 3 hours ago. Finally got resolved. This is what happens when it rains in LA. Doesn't matter, though, because I'm here now, man. And we got a big stream in store. Because there's a new Jump King map. One of those Jump King maps that only the real ones play. Only the GOATs, not for the faint of heart. And today we're one of the ones who are going to play it. Hold up real quick. I'm trying to see if Sentinels is going to clutch up against Leviathan. Real quick. Just let me just take a peek. I just want to see if they go OT. That's all I care about. It looks like it's an OT moment. Uh-oh. 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 Oh, no. Alright, he died to a fucking molly. Okay, I don't need to watch it anymore. Alright, chat, today we are doing the new Jump King. Saw you on Jody's stream, you were not ready. I was ready, bro. Binge watching your Among Us videos waiting to this stream. Movie pair, this is going to be whiplash if you're coming from Among Us to Jump King. Because in Among Us, I don't shut the fuck up. In Jump King, I'm going to go non-verbal. Okay? Just get that expectation out of the way there. Before we dive into it, chat, come on, man. Come on. How we doing today? Can I get a vibe check? How we doing, man? How's everybody doing? Thank you for the 27 once again. Bepper Liam Allen. Thank you for the new membership. 6.9 out of 10. Dude, honestly, my day started off on the wrong foot. My internet was out. I went to reset the modem. I broke the light bulb in the room where my modem was broken. I was like, what the fuck is this? Yesterday, I went to do a bunch of chores. I did a bunch of chores yesterday. I tried to pick up the book. This is a mistake. I tried to pick up the book for our book club. All right, if you don't know the Parasocial Club, we got a book club. We're supposed to read I Am Not a Serial Killer. I go to pick it up, but I go to an LA book club, or not a book club, bookstore. And let me tell you that it's a liberal stronghold, which is great. It's wonderful. Okay, it's fine. But the moment I enter, I'm not even in the store yet, I get stopped by a lady who says, "You look like you care about nature." And I was like, "Well, yes." A spot-on analysis. She goes, "Can I have 30 seconds of your time?" And I'm already stressed out, okay? You know what? How about I start up let me start up Jump King gameplay, then I'll tell you about this. You know what? I might as well. Hold up. Let's be smart about this. Let me jump into the map. Then I'll tell you about my day. I'll tell you about my bookstore. Not my bookstore Riz, but thank you to 10 gifted Forest. Appreciate that. Thank you to 25 gifted 25 months. Taito Jedi Live with the 23 months. New Jump King. All right. So here it is. Jump King is a game that I am known for playing, right? Every new Jump King I play, there has not been a new Jump King, though, in a while. And when I say a new Jump King, I mean from Nexile Games, the developer of Jump King. It's been a few years, in fact. However, there are fan-made maps. And recently, a new map dropped. And I'm just going to show you the trailer. It's called Super Jing World. Shout out Valmerix. Lee, thank you the 50 gifted, dude. Holy shit. The king has fallen. Jesus Christ. Badly injured. The king can no longer reach the babe. Jesus Christ. Who can finish this quest now? Buckle up. Lock and load. We got a gun? We have a gun? Jump King Eternal. What? Wait, who does this little character look like? Can someone get me there? What does this look like? It looks like you. Wasn't really thinking that. Snoopy? A brand new adventure! I guess the character's name's Jing? No, this is certainly not official. I think they'd get sued off the planet. Sheesh. Ogre donated 50? Wait, yo, I'm Ogre, the creator of Super Jing World and the creator of Jing. Hope you enjoy the mod and thank you for playing it. Wait, what the hell? Thanks for making the map, Ogre. I hope you don't get sued. And I hope this stream and consequent video does not result in that happening. Legally, you have to say hashtag ad. I guess I did get $50. So a new Jump King map dropped. And this is not an official map. I want to clarify. This is a fan-made map. But the last time we played Jump King was also a fan-made map. And recently, the fan-made maps have been, I'm going to say it, as good if not better than the actual dev-made maps. And it's not just me who's saying these are great maps. I got a DM from the creator of Jump King, Nexile Games. And I'm going to leak DMs here, okay? Don't want to get on my Carl Jobs, but forgive me for a moment. It says, bang, Super Jing World launch trailer. We got surprised by the creator of Babe of Ascension dropping a big new map project on our Steam workshop. Figured you might want to hear about it. Sunglasses emoji. They put some crazy effort into a trailer too, we noticed. And then I asked a simple question. You think a young pup like me can beat it in a few hours? And they said, good question. I tried it last night. The others haven't yet. And got a bit into the last world, World 6, in 2 hours. I'd say it's doable in a few, but I won't swear it on my life. So they're flexing, right? The dev of Jump King's flexing. In 2 hours, I got to the last section. Maybe you could do it in a few. So the goal today is simple. I want to be better and faster than the dev. Challenge accepted, baby. Super Jing World will be defeated in not just a day, but in a few hours. Let's throw the timer on the damn screen. Let's get to it, baby. Thank you, the $50 dries. Hello, Mr. Lotto. We've been enjoying Unpaid Intern, but was wondering why the set changes for episode 2. Kind of felt like it was that one friend who had to sit in the back of the class because there wasn't enough room for the cool kid table. No, hey, just curious. I liked it better than episode 1. I think the way the guests had to sit in episode 1 was kind of awkward. They felt awkward to me. Lee, thank you again for the... Is that 100 gifted from Lee, or is that 50 gifted? I can't... Sometimes it doubles. Lee, thank you very much for the 50 gifted. Or 100 gifted. Thank you. Kunar, a lot of you guys spend my rent money. Why? And how is your rent $5? Magic Triangle, thank you for the 4 months. Thank you for 20 Megan. Brian the boy. I beat it in 15 minutes. You could probably do it in 12 hours. These motherfuckers are so cocky, bro. $100 from Urban Winter. I am him. I mean, you gave me 100. I'll agree with you. Thank you for 5, Audrey. It's my 19th birthday. If you don't beat it in 4 hours, will you do the Luddy? Yeah, I'm not worried about that. I'm not going to do the Luddy. 4 hours? That's easy. That is light work, Audrey. Thank you for all the memberships, everybody. Let me boot up the game. Let me boot open the game so the people who are looking at the title and the thumbnail don't go, this isn't Jump King. I got it, man. I got it. Relax. Jumbled. Thank you for 22 months. Sad Smiley. Thank you. Bookstore story. I'll get there. I'll get
Yo. Dumbass. Work. You got paid today? Say? Weird. Oh, what the fuck? Wait a sec. Bang. Oh, the sofa. Dude, what the hell? There's so many perks. What happened, man? Just one of those things you don't uninstall, man. Keep updated just in case. Like League. No, man. Still play ARAM. Oh, dude. It takes like... yeah. Like the individual game files, like player profiles, are so large. Oh, okay. Yeah, are you going to the dispensary? You know what deals they have? I was gonna see if you could pick me up stuff while you're there too. I need a Stizzy Pod, a plug and play, and oh yeah. Yeah, I'll send you what I want. So you're going to Ash? Are you gonna smoke if they offer you? Are you gonna like smoke if they offer you? You know, sometimes they offer you to smoke inside the store. Dude, well, I think the store went pretty ratchet. No, not Ash. It was like one of those like underground ones where like you gotta like, but the deals are super cheap and they were just like passing a joint around to everyone else like I'm good. The deals they have are like super cheap, but it's like I still want to like wait in line. Owners around, weird people. Yeah. The only time they would leave the house together, like. Okay. Play. Dizzy Pod. What are you planning to get? Hell yeah. Oh, you see that right now. Is it Potter? Cheater? What is the Jeters? Is that like a pot or something? Oh, the 510? Those ones are pretty lit. We'll get hella fucked up Saturday. We'll do edible. Then we'll the edible